Okay, we have studied what is meant by capacitor, and we have studied how to calculate the capacitance of simple capacitor shapes like parallel plate capacitor and coaxial cylindrical capacitor and concentric sphere capacitor. And then we studied what will be the effect of connecting the capacitors in parallel and series. Now we are going to talk about the energy stored in the capacitor. And this energy stored is basically stored in the electric field inside the capacitor. So effectively, to charge a capacitor, it means that we are moving negative charges from the positive plate to accumulate them on the negative plate. So the positive plate becomes positive and the negative plate becomes negative. To move these charges, actually you are doing work. So this work is stored as an energy inside the capacitor. So there is work must be done by an external agent to charge a capacitor. We can imagine doing this work ourselves by transferring electrons from one plate to another one by one. Effectively, as the charge is built up, as we transfer negative charge from the positive plate to accumulate them in the negative plate, there will be electric field built up. This electric field introduce additional force. This additional force will introduce more extra work to be done to move any extra charges. So as the charge is built, so does electric field between the plates, which opposes the continued transfer. So in this case, greater amount of work are required to move extra charges from the positive to negative plate. Actually, we don't do this job by ourselves. The battery is doing this, but on the expense of its chemical energy. So the chemical energy inside the battery is transferred to electrical energy stored in the capacitor. The question now, we have known that when a battery with a potential difference V is connected to a capacitor, there will be flow of the charges in this circuit until the capacitor reach the potential of the battery itself. So the potential difference at the full charge on the capacitor will be V, which equals the voltage of the battery. So now we have potential difference V on the capacitor, and we have known that the total charge in the capacitor Q equals C multiplied by V. So we know the potential V, we know the charge. The question, what will be? To calculate the stored electric energy in this case, suppose that at a given instant, a charge Q dash has been transferred from one plate of the capacitor to the other. So incremental charge Q dash will introduce a potential difference V dash between the plates. This V dash is actually related to Q dash by the value of the capacitor. So V dash would equal Q dash over C. Now, in terms of incremental delta Q, if any extra delta Q is moved, and we have a potential difference V dash, so for moving a charge delta Q dash inside a potential V dash, the required work delta W would be the incremental charge multiplied by the potential difference or the electrical potential. So we said in last chapter The work is Q multiplied by V. The work or the electrical energy or the electric work done equals the electric charge multiplied by the electric potential. Now, V equals Q dash over C. By integrating the total work done, we integrate over all the charge which is accumulated on the capacitor. So, in this case, by integrating both sides, we can obtain the total work done equals 1 over C integration of Q dash d Q dash from 0 to Q, where 0 is the initial charge on the capacitor, which doesn't have any charge, to the final value of the charge Q. Q dash dq is Q squared over 2. So the total work done to transfer charge Q from positive plate to negative plate in the capacitor to charge the capacitor is Q squared over 2C. This actually the derivation of the total stored energy in the capacitor. Now, we can replace Q by CV. So, in this case, if we set that Q equals CV, so the total stored energy in the capacitor would be CV squared over 2C. It will be half C multiplied by V squared. So this work is stored potential energy in the capacitor, U equal Q squared over 2C, and since Q equals CV, so the total stored energy in the capacitor would equal half CV squared. The potential energy of a charged capacitor can be viewed as being stored in the electric field between its plates. So if we are talking about parallel plate capacitor, so the parallel plate capacitor, if we remember, it was epsilon naught multiplied by area over the distance between the two plates. Now we have calculated the stored energy in a capacitor. The question now is, what is the energy density inside the capacitor? Energy density here is the potential energy per unit volume. Assuming that we are talking about a parallel capacitor, the parallel capacitor is composed of two plates, each plate with area A, and they are separated by a distance d. So the volume of this capacitor is A multiplied by d. Now, by dividing the stored energy in the capacitor by its volume, we obtain what we are calling energy density. So, in the parallel plate capacitor, neglecting fringing, the electric field has the same value at all points between the plates, thus the energy density between the plates should be also uniform. We can find the energy density small u by dividing the total potential energy by the volume AD of the space between the two plates. So, in this case, the energy density would be the total stored energy divided by the volume of the capacitor. The total stored energy is half C multiplied by V squared, and the volume is A multiplied by D. If we remember, the capacitance of parallel plate capacitor was epsilon naught multiplied by the area of the capacitor over the spacing between the two plates. So, in this case, if we replace the value of C here by the value of C here, so we can find out U, or the energy density, epsilon naught A over D multiplied by V squared over 2AD. So we can replace this A with this A, and this D with this D will be D squared, so it will be half epsilon naught v squared over v squared. But if we remember, the electric field between two parallel plates in terms of the potential difference between the two parallel plates is minus V over D. So the value V over D can be replaced by the value of the electric field. So in this case, the stored electric energy density would be half epsilon naught E squared. And the unit of this energy density is unit of energy per unit of volume. So it is joule. Now, as an example, an isolated conducting sphere whose radius r is 6.8 centimeter has a charge Q equal 1.25 nanocoulomb. How much potential energy is stored? Here, I'm talking about the total potential energy, capital U, is stored in the electric field of this charged conductor. So to calculate it, we said that the stored energy can be Q squared over 2C or can be half C multiplied by V squared. In our case, we have Q and we have the radius. So from the radius, we can calculate C. And now from Q squared over 2C, we can calculate the potential energy. We can calculate the stored energy in this system. This is the capacitance of isolated sphere 4 by epsilon naught r, and potential energy can be calculated either by Q squared over 2C or half CV squared. In our case, it would be more suitable because actually we have already the charge, not the potential. It would be better to use this for Q squared over 2C. So we'll calculate C. C is 4 by epsilon r. So Q squared over 2C, Q squared over 2 multiplied by 4 would be 8 by epsilon naught r. And we will replace Q by 1.25 nanocoulomb, 4 by, or sorry, 8 by here, 8 by epsilon naught, and r is 6.85 centimeter, so it would be 0.0685 meters. By calculating this value, we can obtain that the stored or the potential energy in this sphere would be 1.03 multiplied 10 to the power minus 7, or 103 multiplied by 10 to the power 9, so 103 nanojoule. Okay. Now the same isolated conducting sphere whose radius r equals 6.85 centimeter and charge Q 1.25 nanometer. What is the energy density at the surface of the sphere? Energy density, small u, is half epsilon naught E squared. So it is required now to determine E squared, or E, the value of the electric field at the surface of the sphere. So to calculate the electric field at the surface of the sphere, we will return back to Gaussian law. Imagine this is the sphere, and we have a Gaussian surface surrounding the sphere. So we will calculate the electric field on the sphere. We can obtain that the electric field in the sphere would be, outside the sphere is Q over 4 by epsilon naught r squared, and we will replace r with just the surface of the sphere, 6.85, centimeter. So we can obtain the electric field. So the electric field is 1 over 4 by epsilon naught q over r squared. Now, by using this electric field to calculate the energy density, so U equal half epsilon e squared 1 over 2 multiplied by e squared. So this 4 would be 16. So 16 multiplied by 2, it would be 32 by squared. And we have epsilon here and we have epsilon squared here. So we have only epsilon here. Q squared over r to the power 4. Now by substituting, Q would be 1.25 nanocoulomb, R would be 6.85 centimeters, would be 0.0685 meters, and the remaining parts are constants. So by this, we can obtain the energy density, and the unit of energy density is energy joule per meter cube. And we can replace 10 to the power minus 5 by 6 to be microjoule, so it will be 25.4 microjoule. Now, as a review question, I'm saying that a certain capacitor has a capacitance 5 microfarad. After it is charged to 5 microcoulomb, so I have charged with a charge 5 microcoulomb, and isolated. So it is fully charged and the value 5 microfarad. The plates are brought closer, so its capacitance becomes 10 microfarad. So I have nearby the plates to increase the capacitance. The capacitance is increased from 5 to 10 microfarad, and the charge is the same because it is isolated. Now, the work done by the agent to do this job is about 0 joule or 1.25 microjoule or minus 1.25 microjoule or 8.3 multiplied 10 to the power minus 7 joule or minus 8.3 multiplied by 10. Question 2. Now the quantity half epsilon naught e squared has the dimensions of what? I have repeated it many times in the lecture. Energy per farad, energy per coulomb, energy per volume, energy per volt. Which one? Hopefully you do it correct. Okay. A charged capacitor stores 10 coulomb at 40 volts. So its stored energy is what? You will just use the law of energy storage. Sorry, yeah, you have 10 coulomb is charge and 40 volt the voltage, and it is required to find out the stored energy. It is 400 joule, 200 joule, 4 joule, 2.5 joules, 1.25 joules. It's just simple calculation. Now, assume that Q denotes charge and V denotes potential difference and capital U denotes the stored energy. Of these quantities, capacitors in parallel must have the same what? Only Q or only V or only U or Q and U or V and U. So if the capacitors are in parallel, doesn't mean that capacitors are the same, any type of capacitor or any values of capacitor, but are in parallel. And we have Q, V, and U. So which one should be the same for this type of connection? Now, a battery is used to charge a parallel plate capacitor, after which it is disconnected. So the capacitor now is charged. Then the plates are pulled apart to twice their original separation. So we have increased the separation between the two parallel plates to the double value. This process will double what? Capacitance, save the charge density on each plate, store the energy, electric field between two plates, charge on each plate, each one of them. Okay, best wishes and see you in the next lecture.